So we're going to be looking at conservation of energy in this lesson. So we'll look at a couple different examples where conservation of energy will be important, and then we'll look at conservation of energy in collisions. Okay, so our bell ringer question. We want to list 3 different types of energy besides kinetic and potential energy and give an example of each of them. So I have one example written here, so it's kind of helping you out. An example of thermal energy would be combustion of coal in a steam engine. Alright, so a couple more examples of energy would be electrical energy. So you could say there is electrical energy that comes from the outlets in our houses, or electrical energy is generated by power plants through the thermal energy process of burning coal. We could also have solar energy. Alright, so this would be radiation converted to electrical energy. So solar energy, if photocells are going to store energy in batteries. We also have nuclear energy. So these are just a few of them that we could list. So we have some nuclear power plants that generate energy. So that nuclear energy is turned into electrical energy, which is sent to houses. So there's just a few examples, and there are more. You can look them up. So a question to be thinking about throughout the lesson is, can energy be lost? And you might remember this from your physical science class, the answer to this question. But we'll be talking about this, we'll be discussing this throughout the lesson today. So think about that. Can we lose energy? So we have this law called the law of conservation of energy. The law of conservation of energy states that in a closed, isolated system, so hopefully we remember these pieces here, energy can neither be created or destroyed, rather energy is conserved. So thinking about that question that we just had, can energy be lost? Well, this tells me that no, it can't, but it's going to be conserved, and it might be changed into different things. So in this question, we have to kind of think about what is a closed, isolated system. So that means we're going to consider all forces acting on an object and disregard wasteful things such as friction. And really, a closed, isolated system, if you have like a car here going that way, a car here going that way, we're not going to think about drag working on the car. We're not going to think about friction on the wheels. Okay, we wouldn't consider, you wouldn't think about like a little bug in the situation or something like that. We're just going to be looking directly at the cars and the energy that the two cars have going together. Okay, so we would disregard friction and air resistance, which is essentially friction due to fluid, because those are considered wasteful things for energy. So a little bit more about the conservation of energy. So the sum of all kinetic energies and potential energies, that is called the mechanical energy. Okay, so that would be everything together. The system's mechanical energy is both kinetic energy, which is 1/2 mv squared, and potential energy, which we're going to be talking about gravitational potential energy, which is just mass times gravity times height. So kinetic energy, if we were looking at a system with translation and rotation, we would have to figure out both of those. That would be the total mechanical energy of the system. And so remember, for rotational kinetic energies, that's going to be 1/2 I omega squared. So it's going to be half the moment of inertia times the rotational velocity. And our potential energy is going to include gravitational and elastic potential energies. Now, we don't necessarily have an equation for elastic potential energies, but gravitational we do. That's mgh. The elastic potential energy really depends on what you're looking at. Are you looking at a spring, or are you looking at something rubberized, or are you looking at a combination of the two? So elastic kind of depends on what you're looking at. So our general equation for mechanical energy of a system, okay, this is mechanical energy, is going to equal our kinetic plus potential energy. So when we're looking at mechanical energy and conservation of energy, if we have both of these in the beginning, then this would be considered maybe the initial energy. And then again at the end, we'd have to calculate that energy in the end, which would be our final energy. So in general here, we have our conservation of mechanical energy. If, like I said, we have kinetic and potential in the beginning, we would have initial values such as this and set them equal to final values such as this. Okay, and we can draw a bar diagram about these energies, so that might be a better way to explain it, like which is more, which is less at certain points in time. So here would be an example of a simple bar diagram. So in the beginning, if I try to make some sense of this bar diagram, I have more potential energy than I do kinetic energy in the beginning. So this kinetic energy here tells me that I'm moving, and this higher potential energy tells me that maybe it's something that's stretched out, like a spring, or maybe it's like a rubber band that's kind of stretched out, or if I'm thinking just mass times gravity times height, maybe in like a roller coaster scenario or something like that, I would be higher up here than I would here in this scenario. But in order to talk about this, we have to compare our initial versus our final. Okay, so as we go from this side, the initial side, to the final side here, you can see that our kinetic energy increases and our potential energy decreases. So if we're talking about gravitational potential energy, then this would be closer to the bottom or closer to our reference point, and the object is going to be moving faster. But if we wanted to calculate total energy, so I'll kind of show you here how that total energy looks, you would just add the two together. So if I draw a box around this one, and I would put that on this piece here, okay, then you can kind of see that that equals my box for total energy there. And if I took this and put it on this one, okay, because it looks like they kind of pretty much switch over, then you can see that my total energy is going to match what it should. Okay, so you would find a total energy just by adding my kinetic and potential energy in the beginning, and then you could say that it must be the same here, so you add kinetic and potential energy in the end. So I have a couple examples here that we want to look at, and I'm not going to read through everything. I'll just kind of describe the situation here, and you can read through this if you want to. So I have a roller coaster in this example, and then we have a pendulum in this example, and I have a bar graph that goes with it. So you can kind of make some sense of this. So in the beginning we have a roller coaster. This is position A. He's way at the top. So if we consider the bottom here our reference point, then I can look at every single position here. So my gravitational potential energy is going to be the highest at this point because I'm the furthest from my reference point. All right. So we are moving a little bit at this point, so there is going to be some kinetic energy. But then as we move forward, we start to go down the hill. So this is going to reduce my gravitational potential energy because my height is reduced from where I started. Okay, and that will increase our kinetic energy because gravity's pulling on that and it's going faster. All right, so then down here, I'm going to have quite a bit of kinetic energy because I'll be going a lot faster, and my height is reduced, so my potential energy is going to be much less. Okay, so if we compare this to this one, potential energy is going to be way down because I'm a lot closer to my reference point. All right, but I'm still moving and I still have height compared to my reference point, so I have both gravitational potential energy and kinetic energy there. Okay, so we have kinetic energy and potential energy throughout the entire thing at each point. So we could compare scenario A to scenario B. Say if we knew the energy here, then we could figure out how fast this car was going if we had the height. Same thing here. If we knew the energy at the beginning, then we could find how fast the car is going down here at the bottom if we knew the height. So that's the benefit of using different kinds of energy or potential and kinetic energy to solve these types of scenarios here. Same thing goes with the pendulum example. So you have different positions here, A, B, C, D, E. So this position here would have a greater potential energy than this position because I am further down, closer to my reference point. And maybe we could say the reference point would be the ground or something like that. Or we could say in a pendulum that this would be my reference point, the bottom of the swing. So I have potential energy. I have both here, potential and kinetic here, and then I have zero potential here because my pendulum is at my reference point, but it's all kinetic energy here. And then it just kind of transfers back to potential energy as it returns to its height. So A and E are both going to have all potential energy, and really this is going to stop a little bit, stop for a quick second there, or a quick, I don't know. So really this is going to stop for a brief moment in time right there, and then it's just going to transfer back and going to go back to where you started. So a pendulum is a really easy way to see that we have potential energy turning into all kinetic energy and kinetic energy back into potential energy, and it just kind of flip-flops the whole time. It goes back and forth. So let's try to use our energies here to solve a problem. So we have a 22 kilogram tree limb, 13.3 meters above the ground, and during a storm it falls on a roof that's 6 meters above the ground. So here's the picture here. So our tree branch is originally up here, and the storm comes through and it falls 6 meters, or it falls to a point 6 meters above the ground. So we have A and B. We want to find the kinetic energy of the limb when it reaches the roof. And then for B, we want to find the speed when it hits the roof. So at the beginning, we're going to say, let's write out our mass as 22.0 kilograms. And let's say our reference point is going to be that 6 meter line, or the house. Okay, so our original height, if we're comparing it to the house, we're going to have to do a little bit of subtraction here. So what's the original height compared to that reference point? So our original height, if we subtract those two, 13.3 minus 6 is going to be 7.3 meters. So we're 7.3 meters above the house. And we could use the 13.3 and the 6 if we wanted to, but this is going to make it a little bit easier. This will make our calculations a little bit easier. So if we write out our mechanical energy, or conservation of mechanical energy equations, we're going to have kinetic energy initial plus potential energy initial is going to be equal to kinetic energy final plus potential energy final. So in the beginning, the tree branch is up here, not moving. We don't have any kinetic energy. And then in the end, since we called the roof our reference point, that would be zero, a zero height. Since that's our reference point, we don't have any potential energy. So really, this is going to be the equation. We have our initial potential energy is going to equal our final kinetic energy. So let's write it out. So we have mass times gravity times height for that potential energy. 1/2 mass times velocity squared for that kinetic energy. And this is kind of nice. If you see on the left and the right, we have the same mass. So that essentially does not matter. Okay, so let's plug into our equation now. All right, so we got 9.8 meters per second squared for gravity. And we got a height that we wrote down was 7.3 meters because that's above our reference point. And then we have now, since that mass canceled out, it's just 1/2 velocity squared. And I'm working ahead a little bit. This is going to allow us to calculate the velocity. But really, when we hit that roof, like we said here, our kinetic energy and potential energy are going to be the same. So the answer for A is just going to be these two multiplied together. And then for B, we can use this part of the equation to solve for the velocity when the tree limb hits the roof. So let's do this part here to find our kinetic energy. So since we said that potential and kinetic are the same, so this is essentially our potential energy, but it's going to be equal to our kinetic energy, which is going to be 71.54, and that is in joules. So that's for A. And then if we wanted to use this for our second part, I'll write it down here just so it's in the correct area. 71.54 joules equal to 1/2 velocity squared. So a little bit of algebra here. Times both sides by 2 to get rid of the 1/2. and then we're going to have to square root both sides to get our answer for velocity. So 2 times 71.4, and then we square root that, and then you'll get a velocity of 11.96, and that label is meters per second. So the velocity of that branch when it falls towards the house is 11.96 meters per second. And if we wanted to kind of prove that this actually works, let's use some stuff that we remember or that we've done before. So we can use kinematic equations to do the same thing here. And this is the kinematic equation that we want to use just because these are the variables we have. So with this one, the initial velocity of the branch is 0, so that's gone. So really we'll have final velocity squared equals 2a delta x, which we'll have to square root both of these to get our final velocity. And when you put the values in here, so 2 and then 9.8, and then our delta x is going to be that height, so we're falling 7.3 meters until we hit the roof, you are going to find out that we get exactly the same value. We get 11.96. We get 11.96 meters per second, which is kind of cool, so we can show that our energies do the same thing as our kinematic equations. So let's take care of another one. Let's try another example here. So we have a mass of a diver, steps off a 5-meter diving platform. We're going to ignore air resistance. What is the kinetic energy and velocity of the diver as she enters the water? So we're just going straight off that diving platform. Okay, so diver, diving platform, and we're at 5 meters above the water. So we want to find the kinetic energy as we hit the water. So we can draw out our equation. Kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. Think about what we have in the beginning. Diver is just on the board right there, not moving, so we have no kinetic energy. And then in the end, we'll say that that 5 meters, the bottom there, is our reference point. So in the end, we don't have any potential energy. So we're left with something like this again. So this is just mass times gravity times height. This is 1/2 mv squared. Just like up above, you can see that the mass is negligible here. We don't need it. So let's just write out what we need. So we got gravity, and then we're going to have a height of 5 meters. And then we're going to have our 1/2. Mass cancels out. We're going to have a velocity, which we're trying to find. So it'll be just like we did last time. So to save ourselves some time, we can do some algebra, move that over there, right? Multiply both sides by 2. That's how we get that over there. And then we'll square root both sides to find the velocity. Okay, so we're going to get a final velocity of 9.899. So let's just call it 9.9 meters per second. So the diver is going 9.9 meters per second as she hits the water. So that's how we use our conservation of energy equations to solve for energies and velocities. So if you have these things at home, you want to find a small rubber ball and a large rubber ball, like a bouncy ball, maybe a little rubber ball, or a little bouncy ball and a big bouncy ball. If you have maybe a small kickball and a big kickball, you're going to take them and you're going to put the small one on top of the big one and try to drop them simultaneously and see what happens. So if I line them up, let's say we have the little one there and the big one there, kind of looks like a snowman. We drop them both at the same time. So this is more massive than this one. So this is going to have more potential energy and kinetic energy when we drop it than that one, just because it's more massive. So when we drop them, let's say we got a table down here. They're falling. They hit right here. The big one hits the table with the little one on top of it. Okay, so we have our collision there. What you're going to find is that little ball should bounce quite a bit higher because the energy from this ball is getting transferred to that ball through the collision there. So it's actually kind of cool when you get it to work out correctly. Sometimes the little ball kind of bounce off in a different direction, but if you get it right and you drop them both directly up and down, you'll see that little one bounce possibly about twice as high, depending on how big that one. If it's twice as big, then the little one's going to bounce twice as high because it'll get that energy from it. Okay, so it's kind of cool when you get it to work out. So with that, we're going to talk about collisions and energies. So when we analyze collisions, we're going to use the motion of the objects just before and after the collision, because if we look at more things than that, then there could be other variables involved, like more friction involved, maybe more drag involved. There's other things in the system. We want to look at what happens directly before and after the collision. So how fast is the car going right before they hit, and how far is the car going right after they hit? So we do that to kind of maintain the closed, isolated system idea, and think about what we talked about in our last chapter, that momentum is going to be conserved, so energy is also going to be conserved. And we mentioned this earlier. Energy can change forms, so sometimes kinetic energy is not always conserved. In general, energy is conserved, but think about what energy would turn into. If we had cars, the two cars crash together, they slam on their brakes, we have friction. What does friction produce? Okay, so if we have the car and it just slams on the brakes, it's kind of, so the car's going that way, brakes are pushing me back that way, and then you'll see like the black marks on the ground. How does that happen? Well, that happens from the heat from friction. It's just burning the rubber off those tires when it slams on the brakes. So that different energy is turned into heat energy. So it's still conserved, it's just turned into different energy. So friction will turn that into heat energy. Okay, so when we talk about collisions and energy, we need to talk about elastic and inelastic collisions. So a perfectly elastic collision will have 100% energy conserved before and after the collision. Okay, so we've done a little bit of work with these with momentum. Depends on the elasticity of that, but usually we look at 100% elastic energy or elastic collisions to say that energy is conserved. But if we have an inelastic collision, that could be where the things stick together, and then there's going to be friction involved, or there's going to be some loss of energy, or not loss of energy, energy turned into different sources. So like I just said, talking about inelastic collisions, your final energy, okay, your final energy is going to be less than your initial energy because there's going to be some energy lost, or there will be some energy transformed into different kinds. Usually those wasteful types of energy like friction and drag or heat. Friction will turn into heat. That's what would happen in inelastic collisions. So let's take a look at a scenario where we have an inelastic collision here. The two cars stick together in the end. We're going to try to calculate energy in the scenario and see what happens. So two cars crash on a slippery road. We got a compact car with a mass of 1,150 kilograms moving at 15 meters per second. So let's say car 1, our mass is 1150 kilograms. Our velocity, initial velocity, is going to be 15 meters per second. Then we have car 2 here. So that one has a mass of 1,575 kilograms, and that one's only going 5.0 meters per second. So they crash, stick together, and we want to find the velocity after the car is locked together. In order for us to find that velocity, we're going to have to use our momentum equations, and it's conservation of momentum, so it's initial momentum equals final momentum. And in the beginning here, these two cars are different masses and different rates. So our initial momentum is going to have to be momentum of car 1 plus momentum of car 2, and then we're going to have to find our final momentum after they lock together. So let's write out our equation. So let's say mass of car 1 times velocity of car 1 plus mass of car 2, velocity of car 2, and then they lock together. So remember the trick to these. We're going to have to add those masses together, and then we can find that final velocity of the system because they lock together so the masses combine. So we can't cancel out masses on these. We actually have to plug everything in. All right, so I'll put everything in here, and then we'll see what we get for the answer in the end. So on the left-hand side of the equation, we're going to get 25,125 kilogram times meters per second. This is our momentum. And on the right-hand side of the equation, we have that combined mass of 2,725. So we want to divide both sides by that 2725, and then we will get our final velocity out of the problem here. Okay, so that's going to give us a final velocity of 9.2, we'll say 22 just to be more accurate, meters per second. So that's for part A. That's when we find out our final velocity of the cars. All right, so when they lock together, they're going 9.22 meters per second. So now for the second one, we're going to have to figure out our kinetic energy, how much it decreased in the scenario. So we got to do our initial kinetic energy equals final kinetic energy. And really, they won't be equal, so we can figure out the difference between the two. So I'm just going to use this for a reference. So the kinetic energy in the beginning, so that's going to be kinetic energy of car 1 plus kinetic energy of car 2 is going to be equal to, or we hope it will be equal to, it won't be, but we'll see that in the end, is equal to our final kinetic energy. So remember, equation for kinetic energy, 1/2 mv squared. So 1/2 mass 1 velocity 1 squared plus 1/2 mass 2 velocity 2 squared is going to be equal to our kinetic energy in the end, which is going to be mass 1 plus mass 2 together, and we need that 1/2 out there. So it's similar to momentum. So 1/2 times mass 1 plus mass 2, that's combined mass, times our final velocity of the system, which we figured that out with the 9.22. So on the left here, I'll plug everything in just like I did over here, and we'll see what number we get. And then I'll plug everything on the right, and then we'll see what we get and see if they are equal and what we get. So when we calculate our kinetic energy on the left here, so this will be the initial kinetic energy, we get 149,062.5 joules. And then when we do the stuff on the right here, so we have 1/2 times the combined mass times our answer from our momentum equation, we get 9.22 meters per second. So then we get 115,823.9 joules. So if we compare those two, those are definitely not equal. But if we want to figure out how much energy is lost in the system, then we just subtract those two. So we're going to minus that 115,823.9, and then we get a final energy, or our energy lost rather, 33,238.6 joules. So this inelastic collision, we lost 33,000 joules. So let's try another one of these with some ice skaters and see what we get. So we have a 54.5 kilogram ice skater moving at 3.2 meters per second collides with a 44.7 skater who is motionless. So that'll make the calculations a little easy there. They then slide together along frictionless ice. What is their velocity after collision, and how much energy was lost in the collision? So what fraction of original kinetic energy was lost? We got a little bit more for this one. So let's use momentum to figure out our final velocity. Okay, so we have initial, let's say initial for the first guy plus initial for the second guy. Let's say 1, 2 is going to be equal to our final momentum. And the initial momentum for the second person, let's say that's the person in blue, is a 0 because he's motionless, he's not moving. So really our total momentum for the beginning, let's say the 54.5 is our number 1 person, and then the 44.7 is our number 2 person. So momentum in the beginning is just going to be 54.5 kilograms, so it's just mass times velocity times 3.2 meters per second. And then our final momentum is going to be their combined masses, 54.5 kilograms plus 44.7 kilograms equal to final velocity, which we will solve for. Okay, so we'll divide both sides by that 54.5 and 44.7, which is 99.2 kilograms. So divide both sides by 99.2 kilograms. and then we get a final velocity of 1.76 meters per second. So we'll just go to 7.6 to be accurate. So that's our final velocity. So now, similar up above, we're going to have to do our mechanical energy. So kinetic energy initial and kinetic energy final. Since it's asking how much is lost, we know they're probably not equal, but we'll just do it the same here. So in the beginning, this is the only person that has kinetic energy. So that's going to be 1/2 times the mass of my first skater times velocity squared, so 3.2 meters per second squared of that first skater. So this will be our initial kinetic energy because the other person is not moving. And then our final kinetic energy is going to be their combined mass, which was 99.2 kilograms, times their motion at the end, which is 1.76 meters per second, and that quantity will be squared. So we'll get these two values, and then we'll subtract them and see how much is lost. So for our initial kinetic energy, we get 279.04 joules, and then our final kinetic energy is 153.64 joules. And again, we can see that they are not equal. So this is the kinetic energy in the beginning. So we've lost about 120. Let's subtract these two to figure them out. So 279.04 minus 153.64. It's going to give us 125.4 joules. So that's how much we lost in the collision. Okay, so we want to figure out what fraction of the original kinetic energy was lost. So we're going to do 125.4 for that part. 125.4 joules divided by 279.04 joules. So we'll just divide those two, and then we get 0.449, or so 0.45. So 45 hundredths. So it's close to half. So we lose about half the energy in the collision. So really we lost 45% in the collisions. If you want to think about it as a percentage, maybe you might like that. We lost 45% of our kinetic energy in the collision. Okay, so here are a couple examples of how we can kind of look at our conservation of momentum and our conservation of energy. And these are inelastic collisions again because the two objects collide and stick together, and we are losing kinetic energy in the system. So hopefully you know a little bit more about kinetic energy and how we can conserve or lose energy in the system, or how it's transferred to different types of energy. Thanks for watching.